We have two rods, length L1 and L2, and heat coefficient K1 and K2. They are placed like this. Find the heat conductivity coefficient of a equivalent rod of length L1 plus L2. So total length of this equivalent rod will be same as this. And what should be the heat coefficient of that rod that is equivalent to this system of rods? Basically, if you have a temperature differential across this combination of rods, whatever the heat current is going to be, we want the same heat current in this equivalent rod of same length and same cross-sectional areas. So you can see that these two are in series. So heat resistance we know is L by Ka. So if you are unfamiliar with heat resistance, basically we can, just like in the current, we have the current is voltage by resistance. So here also that heat current can be written as in terms of, so voltage is replaced by temperature difference and resistance is replaced by L by Ka. So when you have your term dq by dt is equal to Ka delta T by L, so dq by dt is heat current, L by Ka is resistance. So if you take it this side, so resistance into current is equal to potential difference, and potential difference will be delta T. So heat resistance is L by Ka, and then just like what we do in the circuit analysis, we have, when we have in series, we just add the resistances. So here also, because these two are in series, we are going to treat them as resistors which are in series, and R equivalent is simply R1 plus R2. So R1 will be L1 upon K1 into A, R2 will be L2 upon K2 into A, and R equivalent for this rod will be L1 plus L2 upon K equivalent into A, which gives K equivalent to be L1 plus L2 upon L1 by K1 plus L2 by K2. As an exercise, you can also see that if you have two rods which are in parallel, so what should be the K equivalent of that, of a rod which we replace by that system? Just try that. So there we will use the concept of 1 by R equivalent is equal to 1 by R1 plus 1 by R2. This is a series combination, that's why this equation. All right.